10, 9, ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. Liftoff. We have a liftoff.
Astronauts who went to the moon during the Apollo program traveled on a Saturn V with a launch weight in excess of 2.8 million kilograms. The command module, far less than 1% of the launch mass, returned to the Earth. The shed stages and even the charred capsule could not be reused. Spaceflight was very expensive. In the early 70s, the Nixon administration favored a reusable space transportation system, commonly known as the Space Shuttle. It was expected to reduce costs and provide regular access to space for paying customers.
5, 3, 2, 1, 0, and liftoff of Space Shuttle Atlantis.
NASA had to develop new high-performance reusable main engines, advanced avionics, and a reusable thermal protection system to enable the orbiter to make repeated re-entries into the Earth's atmosphere. Development of these technologies proved to be very challenging. The very earliest proposals for spaceflight had imagined a winged spaceship returning to the ground to be used again. At its foundation, NASA's Space Task Group had inherited the X-15 rocket-powered research aircraft. It was the result of a study made by Walter Dornberger, commanding officer of the German V-2 development program. The X-15 was intended to gather data about hypersonic speeds and very high-altitude flight. Essentially, it was a fuel tank and a rocket motor with short wings and a cockpit. It was fueled with anhydrous ammonia and liquid oxygen, with highly concentrated hydrogen peroxide driving the turbopumps that delivered the fuel and oxidizer. The engine could be throttled by varying the speed of the turbopumps. The X-15 began operation in 1959 as a partnership between NASA and the US Air Force, which was keen to develop a space plane. Mounted beneath the wing of a B-52, it was carried to more than 13,000 meters before it was air-launched. The X-15's engine would fire for around 1 minute. At the peak of high-altitude flights, the pilot had no aerodynamic control. The plane had thrusters for basic maneuvers above the atmosphere. When the fuel was depleted, the craft returned to a dry lake bed in the Mojave Desert. Data gathered during this unpowered return to Earth was of huge benefit to the developers of the Space Shuttle, which had to make similar high-speed, dead-stick landings. Some of the X-15 pilots became household names, including Neil Armstrong, who made 7 X-15 flights, and the aircraft contributed significantly to the manned space program. Yet, even as the X-15 flights continued, NASA and the Air Force began testing a new lifting body concept that held out hope for the shape of spacecraft to come. In 1963, a plywood wingless demonstration aircraft began flights towed behind a Pontiac convertible. They called it the flying bathtub.
3, 2, 1, 0.
At this time, NASA was committed to the ballistic re-entry concept necessary for the blunt body, heat shield type of spacecraft being built for the Mercury, Gemini, and Apollo programs. This meant a fleet of naval ships had to be on standby in each of the major oceans when a spacecraft was launched, which was very expensive. The Kennedy deadline was approaching, and the Apollo program was reaching its climax. The huge and very expensive Saturn V had taken a crew to lunar orbit in 1968, and then both Apollo 11 and Apollo 12 made successful lunar landings in 1969. Apollo missions extending out to Apollo 20 had been scheduled, but at this point the last 3 missions were suddenly cancelled. The White House was back in Republican hands, and the new president, Richard Nixon, although he was keen to bask in the reflected glory of the Apollo astronauts, also wanted to save money.
That this is the beginning of a new era.
After the return of the hugely successful Apollo 15 mission, Nixon tried to scrap the remaining Apollo program, but was persuaded by the director of the Office of Management and Budget to let NASA finish its last 2 lunar missions. It was obvious that NASA's blank check days were coming to an end. NASA and the Air Force had continued to explore the lifting body concept with flight tests of the much heavier HL-10 starting in 1966. It was built to NASA specifications by Northrop. The hope was that a new generation of spacecraft could re-enter the atmosphere and land at a designated strip, saving the costly mid-ocean recovery. The HL-10 was equipped with a small rocket motor and was air-launched, just like the X-15. Telemetry allowed a ground team to monitor the craft's behavior. Ultimately, the HL-10 reached heights in excess of 27,000 meters and a speed of Mach 1.86. Again, the most valuable data gathered during the HL-10 program came from the unpowered return phase of flight. Like the X-15, it dropped rapidly while generating very little lift, just like a spacecraft. When the lifting body program concluded in 1970, it was just one of many concepts being investigated by NASA and the US Air Force. Various companies hoping for lucrative contracts were also submitting designs. NASA had wide-ranging ambitions for the post-Apollo future, but the Nixon administration, which had continued cutting funds for the space program, directed the agency to focus on low Earth orbit with a reduced budget. Some of the scrapped Saturn V launchers were repurposed for an orbital space station that became known as Skylab, while the remaining Saturn rockets became billion-dollar museum pieces. Skylab successfully demonstrated the value of an orbiting laboratory. Pure crystals were grown in microgravity, and a solar telescope enabled new studies of the Sun. But without means to boost Skylab's orbit, it could only ever be a temporary outpost. NASA began planning a more permanent space station for the distant future. Its construction would rely on a new spacecraft called the Shuttle. It might be expensive to develop, but ultimately it would cut the cost of access to space. The various concepts featured 2 stages: a booster that would fly back to the launch site, and an orbiter that would fly back to the ground at the completion of the mission. All were too expensive for the administration in Washington. Finally, a compromise design was reached. Relatively inexpensive solid-fueled boosters would serve as a first stage, and the orbiter would have a huge external tank that would be discarded nearing orbit. But it took years for the concept to be tested to the point where plans could be drawn up. Lockheed had devised a lightweight thermal tile with such promising insulating properties that it made the winged concept feasible. Single-use capsule spacecraft had a heavy phenolic resin heat shield that burned away during re-entry. A reusable spacecraft needed a reusable heat shield, and Lockheed's lightweight silica tiles meant heavy, heat-resistant titanium alloys could be dispensed with in favor of a more conventional aluminium superstructure protected by the tiles. NASA was collaborating with the Air Force on the new spacecraft, and because of military requirements, the design was much larger than most of the early concepts. Work began on the first shuttle in 1974. Initially named Constitution, it was intended for approach and landing tests within the atmosphere. It lacked a heat shield and engines. It was first seen in public at a ceremony as it was rolled out of the Rockwell plant in California. A letter-writing campaign had convinced NASA to rename it Enterprise, after the spacecraft in Star Trek, a TV show that enjoyed modest success at the time. The Enterprise's first trip was by road to the Dryden Flight Research Center. It took 10 hours for the spacecraft to make the 58-kilometer journey to begin a series of captive flights known as approach and landing tests. The Enterprise was unable to fly without assistance, so NASA had purchased a surplus 747 from American Airlines. It had been reinforced with special attachment pylons and extra stabilizers added. At Dryden, a complex framework had been constructed to lift the shuttle onto the back of the airliner. 4 astronauts, in 2 crews, would carry out the first test flights. Fred Hayes had flown on the Apollo 13 mission. His co-pilot was Gordon Fullerton. Joe Engle had made 3 X-15 flights, and his co-pilot was Dick Truly. Enterprise did not have thermal tiles. Instead, it had a dummy fiberglass coating, and it was fitted with a nose spike housing an airspeed indicator. Tests began in 1977. A series of taxi runs, followed by captive flights, were made to confirm designers' expectations. Initially, a tail cone was fitted to reduce turbulence around the rear of the spacecraft. In August, Enterprise made its first free flight. With the carrier aircraft in a shallow dive, the shuttle was easily able to pull away and fly autonomously. The new spacecraft handled well. Four successful free flights followed.
We're at the end of the approach and landing test phase of this program, but it's really not an end at the beginning. It's just a small step really accomplished toward getting the orbiter into space, and then in that aspect, I'm looking forward to more of the same exciting times as we continue on toward that first orbital flight.
Back at the Rockwell plant, a second spacecraft was taking shape. Columbia would be the first space-worthy shuttle. It was being fitted with thermal tiles and the new RS-25 engines. Both were giving trouble. The glue being used to stick the tiles to the aluminium skin of the aircraft was failing within hours. The radically new engines operated more efficiently because of their much higher chamber pressures. But there were developmental problems. Because the shuttle main engines were positioned off-center relative to the external tank and solid boosters, they had to be able to pivot over plus or minus 10.5 degrees in both axes, as the shuttle stack dropped stages and as fuel was depleted. During the first 2 minutes of flight, the major thrust would come from the solid rocket boosters. These too had to have vectored thrust, and the nozzles could move through plus or minus 8 degrees. Again, Columbia had to be transported by road to the Dryden Flight Research Center to be loaded onto the carrier aircraft that would take it to Florida. It was obvious that difficulty with the thermal tiles had not yet been solved. Columbia landed at the Kennedy Launch Center in 1979. While it had arrived with only a partial covering of tiles, tests revealed that even those tiles would have to be removed and reapplied after a densification process. Shifts of technicians working around the clock took 20 months to complete this process. Meanwhile, the first external tank was shipped from the Michoud Assembly Center in Louisiana. It was painted white to protect its outer layer of insulation from ultraviolet damage. By 1980, the shuttle main engines had emerged from their long developmental phase, achieving NASA's specification of 65,000 seconds of testing. Requirements for the engine to be reusable and be capable of throttling down to 65% had been met. The first 3 engines arrived at the Cape and were fitted to Columbia. The original launch date had been delayed by 2 years. At the end of 1980, Columbia rolled out of the vehicle assembly building for Pad 39A. Before it could fly, it had to complete a final certification test that included a 20-second firing of the 3 main engines.
9, 8, 7, 6,
Officially known as the Wet Countdown Demonstration Test, it verified all the systems on the ground and in the spacecraft.
And we have had shutdown of all 3 engines.
Astronauts John Young and Bob Crippen would fly the first mission. It would be the first time a new spacecraft flew with a crew on board. On April the 12th, 1981, Columbia was ready to fly.
T-minus 10, 9, 8, 7, 6, 5, 4. We've gone for main engine start. We have main engine start.
The first 4 flights would all be devoted to testing the spacecraft, and the flight profile for the first mission was designed to minimize stress on the orbiter. The payload bay was empty except for a flight recorder that captured data from an array of sensors. NASA needed to understand the difference between theoretical predictions of the orbiter's behavior and its actual handling. The payload bay doors had heat-dissipating radiators on their inner sides to keep the orbiter cool. When they first opened, the astronauts were surprised. At launch, an overpressure wave had damaged lower areas of the orbiter, including thermal tiles. Young and Crippen maneuvered their craft into a position that allowed a US spy satellite to photograph its underside, but no tile damage could be seen. All the orbiter's basic functions were verified over the 2-day flight, and the craft returned safely to runway 23 at Edwards Air Force Base.
5, 4, 3, touchdown. Welcome home, skipper. Welcome home, Colombia. Beautiful, beautiful.
Colombia's first mission was declared a success, with Crippen and Young having nothing but praise for the new spacecraft. The shuttle was readied for its flight back to Florida, where it would be prepared for its next launch. And there was a long list of worrying anomalies that would have to be addressed before Colombia could fly again. Columbia was towed from the landing strip to the processing facility at the Kennedy Space Center. This first ever preparation of a spacecraft for its second flight to space was to be meticulous. As well as the scheduled tasks, like refurbishing the main engines and checking the thermal protection, the orbiter was checked for damage. Spacecraft tend to evolve. If something breaks or malfunctions, it is not repaired, it's redesigned. Columbia was already lighter than the Pathfinder Enterprise, and engineers building Challenger, the next shuttle, were already incorporating improvements. As a result of anomalies encountered on the first shuttle flight, Columbia and its emerging sister spacecraft were all modified. The most pressing issue was the loss of 16 thermal tiles and damage to a further 148 from shock waves during launch. The shock had bent Columbia's body flap so far out of alignment that engineers were surprised it still functioned. This resulted in extensive redesign of the sound suppression system at Pad 39. A 1 million-litre water tank was built that began flooding the flame pit 6 seconds before the main engines were started, reducing the impact of reflected shock waves. It took 7 months to prepare Columbia for its second flight. The initial aim was to have a 2-week turnaround, but engineers knew there was still a lot to learn about their new spacecraft, and as yet there was still only one shuttle rather than a fleet of 4, which was still taking shape.
Countdown now being conducted by...
The second flight began in November 1981. It was the last time the external tank was painted white. Originally as protection against the sun, the paint was not needed, and leaving the tank its natural orange color saved almost 300 kilograms.
We have the main engine start. And liftoff. Liftoff of America's Space Shuttle, and the Space Shuttle has cleared the tower.
Astronauts Joe Engel and Dick Truly had not flown in space before, and on the ground, Sally Ride became the first female Capcom. While a failed fuel cell caused Columbia's return after 2 days instead of the scheduled 5, the mission was regarded as a success. After 2 more test flights, also with Columbia, the shuttle system was declared operational. Yet there were problems still unsolved. After the second flight, examination of the boosters recovered from the Atlantic revealed an O-ring, used to form a seal between segments, had partially burned through. Tests were made, but designers felt it was not a problem. Pieces of foam breaking free from the external tank were also regarded as a system idiosyncrasy that could be accommodated. by 1985, 3 new orbiters had entered service, making up the full complement of 4 space shuttles. The Space Transportation System was a complex blend of technologies that had to function together with great precision. Together, they were known as the Shuttle stack. The largest component, the external tank, was the only disposable part of the system. It was coated in a spray-on insulation, necessary to keep its cryogenic propellants from boiling. The orbiter and the 2 solid rocket boosters were mounted on the tank. When fully fueled, this was the heaviest part of the shuttle stack. 4 minutes before launch, the main engines went through a final gimbal test. At T-16, the pad deluge system was activated. With 10 seconds to go, the hydrogen burn-off system was activated, and then the main engines ignited. At 0, the solid rocket boosters were ignited, and the explosive bolts that hold the shuttle stack to the pad detonated. At launch, most of the thrust was provided by the solid rocket boosters. Once alight, they couldn't be extinguished. The shuttle's 3 main engines were fed with liquid hydrogen and oxygen through umbilicals near the rear attachment points. After rolling to a heads-down position, the stack would continue climbing along an easterly path till 2 minutes after launch, when the boosters burned out and were discarded. Eight minutes after launch, the main engines shut down and the empty external tank was discarded. It would re-enter the atmosphere and burn up over the Indian Ocean. At this stage, while the shuttle was above the atmosphere, it still needed a further boost to maintain orbit. At the high point of its elliptical path, the orbital maneuvering engines were fired, putting the craft into a circular orbit around 320 kilometers above the surface, depending on the mission. The first 3 years of operational flights saw the new shuttle fleet at the center of the satellite launch business. Almost every mission included at least one satellite deployment. NASA planned to phase out conventional rockets, which it assumed would be priced out of the launch business. During its first 3 operational years, the shuttle fleet deployed 30 satellites. Late in August 1983, STS-8 was the first night launch. The mission went well, and the boosters were recovered from the Atlantic in what had become a routine exercise. Analysis revealed severe erosion of the nozzle on the left booster. Estimates determined it was just 20 seconds away from failure. But it was treated as a minor incident, with shuttle flights continuing to be scheduled at an increasing pace. NASA was encouraging the idea that spaceflight had become routine. In February 1984, Challenger launched with 2 communications satellites aboard. Palapa B2 and Westar 6 were set loose, but the payload assist boosters on each satellite failed. They remained trapped in low Earth orbit. Additional time on every flight was devoted to new techniques made possible by the new system. On STS-41B, Bruce McCandless became the first person to use the new manned maneuvering unit. Since the Gemini program, attempts had been made to have an astronaut fly in space independently, but they were abandoned because of the danger. Several missions later, Discovery was to deploy 2 more satellites. Lloyd's of London had partially funded this flight. As the insurer of Palapa B2 and Westar 6, the company had met its obligation to its clients and now owned the wayward satellites. Previously, they would have been space junk, but NASA would use the MMU to retrieve the satellites and bring them back to the ground. Engineers feared a collision between the shuttle and the heavy satellite, so the idea of approaching Palapa B2 using the manned maneuvering unit felt like a good solution. Astronaut Dale Gardner carried a capture ring that enabled him to slow the satellite's spin. The plan called for Palapa to be grappled by the shuttle's robotic arm, but this proved difficult. The spacewalkers had to improvise. It was brought into the cargo bay by human muscle power. Westar 6 was captured the same way. While the recoveries were successful, NASA decided that brute force capture method was too risky. Subsequent missions began attaching an astronaut to the robotic arm via foot restraints.
Seconds until touchdown.
Discovery returned to the skid strip at the Kennedy Space Center, the first time satellites had been brought back to the ground. In 1985, Atlantis became the 4th and was expected to be the final spacecraft in the Shuttle fleet. In that year, the greatest number of shuttle flights, 9, were made, and it was expected that the rate of shuttle missions would continue to accelerate. NASA was confident that ongoing issues with damage to the thermal protection tiles and the shedding of insulating foam from the external tank were understood and were more of an annoyance than serious problems. In California, facilities at the Vandenberg Air Force Base were being readied for shuttle flights. The site was ideal for launches to the south for polar orbits that were useful for intelligence satellites. The military was impatient with the slow rate of shuttle launches, and pressure grew to keep expendable rockets in service.
Liftoff of Atlantis. A new orbiter joins the shuttle fleet and it has cleared the tower.
Atlantis' first flight was a classified military mission. It deployed 2 spy satellites and was declared a success. Its second mission was notable because the processing between flights was the fastest to date. Again, NASA expected the turnaround time between flights to continue to shrink. Earlier in 1985, Vice President George Bush announced NASA would send a teacher to deliver lessons from space.
Congratulations, Krista McAuliffe.
Yet another sign that spaceflight was becoming routine. Krista McAuliffe and her understudy Barbara Morgan began training for SDS-51L, scheduled to fly early in 1986. McAuliffe was popular with the news media, and NASA was delighted at the positive publicity generated for the Teacher in Space project. The plan called for McAuliffe to conduct 2 lessons from space, including a tour of the Shuttle Challenger. They would be broadcast live to classrooms across the United States. Challenger would launch in mid-winter, and though the Kennedy Launch Center is in sunny Florida, conditions were bitterly cold. In the hours leading up to the launch, engineers tried to convince managers the mission should be delayed. Previous cold weather launches had shown damage to the seals in the solid rocket boosters, but 24 successful missions led management to have faith in the system. Challenger's mission would proceed, though no shuttle had ever launched at such low temperatures.
9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Cameras on the crowd singled out Edward and Grace Corrigan, Krista McAuliffe's parents.
Challenger, go with throttle up. Challenger, go with throttle up.
All 7 astronauts perished. At this point, McAuliffe's parents were still unsure what they had seen. The shuttle fleet was grounded, and moves began to establish a formal inquiry. 3 days after the disaster, President Ronald Reagan spoke at a memorial service for the Challenger crew.
The dedicated men and women of NASA have lost 7 members of their family. Still, they too must forge ahead with a space program that is effective, safe, and efficient, but bold and committed. Man will continue his conquest of space, to reach out for new goals and ever greater achievements. That is the way we shall commemorate our 7 Challenger heroes.
The president was resolute. The shuttle program would continue. The Rogers Commission, set up to find the cause of the disaster, determined that extreme cold had made a seal in the right solid rocket booster fail. But the inquiry also determined that NASA management tended to exaggerate reliability to the point of fantasy. The remaining shuttles were placed in storage, and plans for the Vandenberg launch site were scrapped. There were just 4 American satellite launches for the remainder of 1986 and 87. Major research probes, like the Galileo mission to Jupiter, were postponed indefinitely. Plans were made to return to expendable rockets. There was an extensive redesign of the shuttle's boosters, and every aspect of the space transportation system was scrutinized. Astronauts would return to wearing pressure suits during launch and landing, and a limited escape system was made available.
Go for main engine start. 7, 6, start. 3, 2, 1, 0, and liftoff. Liftoff. Americans return to space.
When Discovery made the return to flight mission in October 1988, it did so with severely diminished expectations. It released a tracking and data relay satellite, replacing the one destroyed with Challenger. It was necessary communications infrastructure for the shuttles and future science satellites. After Challenger, there would be no more deployment of commercial satellites. The shuttle's money-making days were over. There was one positive for the shuttle system. A new spacecraft was built to replace Challenger. It was given the name Endeavour. The second flight after the Challenger disaster was a classified military mission made by the shuttle Atlantis. Launch footage suggested that a piece of a booster nose cap had come away, and Commander Robert Gibson was asked to use the camera at the end of the robotic arm to check for damage.
I said to myself, we are going to die, because I was looking at more than 700 shredded tiles on the right wing of Atlantis.
Gibson was given instructions to land in the usual fashion. Whether flight controllers on the ground did not appreciate the problem or they knew that nothing could be done, remains unclear. Even as it landed, white marks on the usually black tiles suggested damage. The full extent of injuries that Atlantis had suffered only became apparent on the ground. 700 thermal tiles were affected, with one tile in a critical area completely gone. The incident received very little publicity, and the shuttle program would continue. The Hubble Space Telescope had been waiting in a clean room since the year of the Challenger disaster. It was costing NASA and the European Space Agency $6 million a month to keep it in storage. It had been designed with doors that could be opened in space, so it could be repaired and upgraded. It would just fit into the shuttle's cargo bay, and it was completely reliant upon the space shuttle to deliver it to orbit and to carry out routine servicing. On April the 24th, 1990, Discovery sat on pad 39B about to begin its 10th mission. Hubble would finally be deployed.
And go for main engine start. We are go for main engine start, T-minus 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
During this mission, Discovery set a new shuttle altitude record. To prevent rapid orbital decay, Hubble had to be released into a near-circular orbit 615 kilometers above the Earth's surface. There were issues with a sticky solar panel, but this was solved and Hubble was released correctly. Technicians monitoring the telescope soon realized that something was awry. Hubble was returning blurred images. Due to misaligned test equipment, the primary mirror had been ground to the wrong curve. However, engineers were able to design corrective optics. 3 years later, the crew of the new shuttle Endeavour would carry out the repair mission. During preparation for the mission, telescope engineers had analyzed the performance of all the instrument's subsystems, looking to make other improvements where possible. Not only would they fit corrective optics, but they replaced the telescope's solar panels and 2 of its malfunctioning gyroscopes. During the 11-day mission, the payload specialists made 5 spacewalks before releasing Hubble.
Right there!
Astronomers waiting on the ground were jubilant. The billion-dollar piece of space junk became the most important observatory in history. Hubble gave us an accurate figure for the expansion of the universe and its age. It revealed distant galaxies in the finest detail, and it allowed us to see the birth of new stars. Its images were stunning. Shuttle missions continued to visit Hubble, carrying out maintenance and replacing old technology with new, giving the orbiting observatory more than 30 years of productive service, and it remains in operation to this day. Yet in the 1990s, one of the shuttle's original goals remained out of reach. Plans for the all-American space station Freedom had been stymied by Washington. But Russia had been operating their own very large space station, Mir, since the mid-80s. With the dissolution of the Soviet Union, NASA began cooperation with Roscosmos, the new Russian Federation space agency. In 1995, the Space Shuttle Discovery made a rendezvous with Mir. NASA wanted to learn about long-duration space missions. And soon, Americans were traveling in Soyuz spacecraft, and Russians were launching on the Shuttle. On previous missions, Shuttle crews had rehearsed basic assembly techniques. But in 1998, after a new agreement with Russia, the Europeans, and Japan, proper work began on what was now called the International Space Station. What followed was known to shuttle crews as the Wall of EVA, EVA being NASA shorthand for extravehicular activity. NASA had established an EVA office to develop new tools and refine techniques needed for fine assembly tasks. Mission specialists spent months in the training pool, practicing the intricacies associated with their particular mission. In October 2000, 2 Russians and an American launched aboard a Soyuz TM. They took up residence as the first ISS crew, Expedition 1. While they were there, the space station continued to grow as more modules were added. In January 2003, the space shuttle Columbia launched on a scientific mission. "15 days later, it re-entered the atmosphere above California.
Columbia, Houston, comm check. Columbia, Houston, UHF, comm check.
Columbia had disintegrated, and all 7 astronauts were lost.
GC plane. Fly GC, lock the doors. Copy.
Examination of ascent footage revealed a piece of insulating foam had parted from the external tank and struck Columbia's left wing. Debris was collected from Columbia's flight path to understand what had happened, but to some at least, the cause had been known since the launch images had been seen. For a second time, the remaining shuttle fleet was grounded. Building work on the International Space Station stopped, and crews had to rely exclusively on Russian spacecraft. Initially, crash investigators suspected workers at the Mishu assembly plant had poorly applied insulation to the external tank. But formal apologies were made when X-ray analysis revealed that thermal expansion and contraction during filling and emptying of the tank led to cracking of the foam. When Discovery finally launched in July 2005, a brace of new safety measures had been introduced, including more detailed recording of the launch, both photographically and with radar. There was a bird strike, which was of little consequence, but more pieces of foam were lost, and though no damage was done to the orbiter, everyone understood that this was just good luck. From now on, shuttles all carried an extension to their robotic arms, which allowed camera inspection of the lower heat shield. Missions would only go to the ISS where a pitch maneuver was performed, enabling additional inspections to be made by the station crew. If needed, the shuttle astronauts could remain on the space station till a rescue mission could be mounted. Between them, the 3 remaining shuttles would make only 22 more flights. And while its days were numbered, some of the most significant work in its 30-year history was made in this time. Using techniques refined over decades, the ISS moved towards completion, with a crew of 6 permanently on orbit. In 2009, dispensation was made for one special last flight to the Hubble Space Telescope. Hubble was in a different orbit from the ISS, so a second shuttle was ready on the ground should the crew need rescue. Again, the telescope was refurbished with up-to-date technology, and its orbit was reboosted. When the space station was completed, the shuttle retired, again leaving the United States reliant upon the Russian Soyuz to carry astronauts to orbit. While it was partially reusable, this didn't lead to the economies that had been envisaged. However, it was big, enabling it to build the International Space Station and to regularly maintain the Hubble Space Telescope. But the shuttle was never able to realize the standard that its designers had promised, and it failed twice catastrophically, killing 14 astronauts. The spacecraft that was to make spaceflight cheap and routine was unsuccessful on both counts.